Electrochemistry Part 3, Standard Electrode Potentials. The standard hydrogen electrode is something that we use to measure standard potentials. The magnitude of a cell's voltage depends upon the spontaneity of the reaction. So the more positive the cell's voltage will be, the more spontaneous it is, the greater the quote-unquote driving force for the reaction is as it is currently written. That means whether it's being written with an oxidation process or a reduction process versus the other half cell. So for the reaction of zinc and copper, the 1.10 voltage means that the reaction will move towards completion more than the copper-silver cell with the 0.462 voltage, because 1.10 is more positive than 0.462. The zinc-copper cell has a higher potential, therefore a higher driving force than the copper-silver cell does. We can separate the total potential of a cell into the potential of each of the half cells. So based upon each of the half cell potentials, we can get a tendency of one half cell to be an oxidation or reduction process depending on what it's paired with. Now we can't determine the potential for a single electrode by itself because oxidation and reduction occurs simultaneously. From pairing something like zinc and copper, we cannot tell how much of that 1.1 volts comes from zinc, how much comes from copper, what the different relation between them is. So in order to determine these, we actually will just come up with an arbitrary standard. So we base all of our standard electrode potentials against a standard value, and that standard value comes from what we call the standard hydrogen electrode. The standard hydrogen electrode, or SHE, S-H-E, contains a piece of electrolytically coated platinum metal. It is what we call black platinum, and it is coated over the surface with the platinum, and it's caused by fast electroplating in an electrolytic process. So the black platinum tends to be fairly grainy. It provides a highly abrasive surface on which the reaction can occur. The platinum electrode is generally immersed in a 1 molar hydrogen plus solution, something like hydrochloric acid, and will bubble in hydrogen gas at 1 atmosphere of pressure through a glass envelope that surrounds the electrode. So looking at the SHE is an electrode for which the potential is assigned to be 0 volts exactly, so 0.00 infinity zeros. When we look at how the SHE operates, the anode of the SHE is a reaction where hydrogen gas is oxidized to produce hydrogen ion and the release of 2 electrons. The cathode is a process where 2 hydrogen ions will take in 2 electrons and be reduced to form hydrogen gas. So if I look at the 2 diagrams on the right, the first diagram where the SHE is acting as an anode, the electrons are being removed from the hydrogen, and we're going to produce hydrogen ion, which can then move back into solution away from the hydrogen gas, which comes towards the platinum. The second system, we have electrons being brought into the solution where the hydrogen ions are. They are absorbing those electrons, quote-unquote absorbing, producing a reduction process that forms hydrogen gas, which then evolves off. Making the SHE 0 as its reference point allows us to pair it against other half cells to give all of the voltage from the cell pairing to the half cell, which is not the SHE. So we're going to assign all of the voltage from the pairing to the other half cell. Looking at an example of this, if I take 1 molar zinc chloride with a zinc electrode and compare that half cell against the SHE, the initial potential is 0.763 volts. The zinc's mass will decrease as the cell runs, indicating that it is the anode. The concentration of hydrogen ion will decrease, producing hydrogen gas, indicating that the SHE is the cathode. And the half reactions for this process then are zinc producing zinc ions with an assigned voltage of 0.763 volts, hydrogen ion reducing to hydrogen gas with an assigned voltage of 0 volts, for the net total of 0.763 that we observe. So based on this convention, all of the voltage is assigned to the zinc half cell. We add the potentials and we get the overall cell potential. The spontaneity of this reaction occurs in such a way that our oxidation is something like electron pressure. the movement of the electrons is favored from the zinc to the hydrogen rather than from the hydrogen to the zinc due to the nature of the zinc being more easily oxidized than the hydrogen. Before we connect the electrons, it doesn't actually happen, but you can think of like a building up of a supply of electrons, which then, when the connection occurs, flows like a river. Think of a dam. If a dam blocks a river, if there's suddenly a breach in the dam, all that water is going to start to rush from the side which has built up water to the side which is not. And eventually that's going to produce a point where we have level water all the way across, but until that water levels out, we're having a massive rush from the higher side to the lower side. Electrons work the same way. The electrons with greater quote-unquote pressure of electrons will flow from that side to the side with lower pressure of electrons. And so we have from higher potential to lower potential. Looking at the copper She cell, combining copper and She gives an initial potential of 0.337 volts. Gaseous hydrogen is consumed, increasing the hydrogen concentration. The mass of the copper increases. The half reactions are that hydrogen gas produces hydrogen ion with an assigned voltage of 0. Copper is reduced from copper 2 ion to copper metal with an assigned voltage of 0.337 volts. The total voltage is 0.337 volts as observed, with all of the voltage assigned to the cathode in this case, which is copper. The copper's potential is, from the cathode in this case, we're looking at a reduction process in this rather than an oxidation process like we did in the previous one. So here we have all of the electrons flowing to the copper from the hydrogen due to the copper being the cathode with a lower oxidation potential, a higher reduction potential than the hydrogen. The standard hydrogen electrode potential for a half cell then is compared versus the She for a 1 molar concentration or 1 atmosphere concentration. Standard electrode potentials are always tabulated for reduction processes. So the zinc process that we looked at 0.763 volts as an oxidation process will be tabulated and written as the reduction process. By flipping the equation, as we understand, flipping the equation flips the sign of the potential, so we go from a positive 0.763 to a negative 0.763. Compare it to the oxidation process, which had the positive 0.763. Potential measures the tendency for the reaction to behave as a cathode towards the She. If the potential is negative, it will behave as an anode. If the potential is positive, it will behave as a cathode. So positive values act as the cathode, negative values act as the anode. When we write the equations that we were going to pick, we will put cations, hydrogen ions, or elemental nonmetals like chlorine, fluorine on the left, reduced metals, hydrogen gas, or anionic nonmetals like fluoride or chloride on the right.